moving westward while the base of the cloud rapidly moves eastward.
Oh, that's a tornado.
Okay, we got a tornado
That
on the
is a
ground
tornado.
directly to our south.
If you had to guess, what were the greatest causes of mortality due to weather in the United States, and your choices were tornadoes, hurricanes, floods, lightning, heat, hail, what would you put first? Weather is the variable changes in the atmosphere that occur hourly, weekly, even monthly. Climate, on the other hand, is going to be a change which occurs over long periods of time. Take temperature, for example. The highest temperature ever recorded in Ann Arbor was 105 degrees in 1934. The coldest temperature, some 22 below in 1994. Variation on any particular year between highs and lows will be huge. What we're looking for embedded in that is a trend in that, a small trend in the mean temperatures over time. That's climate, the long-term variability in weather. We'd like to explore what is it about these extreme weather events that cause them in the first place, and how are they related to climate? In science, decisions are based on evidence. We must go into the field and make observations, and from those observations we can infer new information. Now in climate we do know that temperatures are rising globally and rising at a slow rate. But there are other things we can't measure, the future for example, and for that we have to use models. Climate models contain the best physics and the best chemistry that we know. And putting those together, we make the best guesses on how our future will change because of changes in the atmosphere. When we think about how temperatures vary over the course of a year, they're like a normal distribution. There's a median value, the temperature which is observed most often over the year, and there are extremes at either end, the very cold days and the very warm days. These are days which occur very seldomly. Our concern is that if we take that whole bell-shaped distribution and shift it to warmer temperatures by just even a small amount, well, it doesn't affect us day to day. If the temperatures are higher by a degree or so on any given day, no one would really care or notice probably. What we are concerned about is the tails, the extreme events. If you take that whole distribution and you shift it a degree or so warmer, then the number of extreme hot events increases dramatically. These are the reasons we're concerned about how a change in global temperatures, a change in temperatures here in Michigan even, could affect extreme weather events, could affect the number of days of very hot temperatures or the temperatures to which the days get to. It seems weather disasters are in the news almost every day. But of all the weather disasters, the one which causes the most deaths in the United States is heat. Heat accounts for about half of all deaths due to weather in the United States. Our greatest concern with heat is during heat waves. These are multiple days of temperatures in the upper 10% of temperatures for a city. And over multiple days, the temperature at night doesn't get low enough for people to have time to recover. In the urban areas, they're more likely to have heat waves because of the amount of concrete and the amount of metal and such in buildings, which traps the heat and causes the urban areas to become much hotter than the rural areas outside the city. This exacerbates the heat effect. We call it a heat island. Detroit, in the map you can see, is much hotter in the center of the city than it is on the outside for those very reasons. Consequently, people who live there are going to be more exposed to the temperature and extremes of temperature than the people who live in the more rural areas. Clearly, not every sunny day is going to be a day of extreme heat. The subset of days which are extreme in temperature are because we have sunlight striking the ground, heating the surface, and then the ground itself is emitting what we call long-wave radiation back into the atmosphere, which gets trapped by greenhouse gases. Carbon dioxide, methane, nitrous oxides, other gases. The atmosphere then re-radiates the heat back down to the ground, and it's that cycling of long-wave radiation from the ground to the atmosphere and the atmosphere back to the ground which is very likely going to be the reason why some days get hotter than other days. It's these very same greenhouse gases that are increasing in our atmosphere, which is why we're concerned about the number of days of extreme temperatures rising. If in fact temperatures are going to rise globally, a real concern for us is how are they going to rise in urban areas. In urban areas, we would expect temperatures could get warmer because urban areas themselves are getting larger, more concrete, more asphalt, more metal. Also, more people are moving into urban areas. So, given that combination, there's reason for concern about how these people and these populations are going to be affected by some increase in temperature due to climate change. So the real question becomes, what can be done? How can we protect these populations from these extreme temperatures? What can be done with our buildings to make them cooler, more naturally? How do we design our buildings to take advantage of natural ventilation and other aspects to make our urban climates more palatable for the future? Another set of extreme weather events that we're concerned about are hurricanes. To understand how hurricanes can be affected by climate, we must go back and look at how they form. We start at the African coast. In Africa, waves come off the continent of Africa called easterly waves, and these waves will form thunderstorms in the North Atlantic Ocean, often beginning in August through roughly October. These waves of clouds are disorganized thunderstorms, but over time these thunderstorms can begin to organize themselves into clusters of clouds, where these clusters can even begin to rotate around a central core, forming a tropical storm. Given enough time, given some warm temperatures in the ocean below, these can form themselves into hurricanes. Inside those thunderstorms, the entire energy which produces the tropical storm and the hurricane comes from the fact that water, vapor as a gas, is condensing into liquid water drops. And that simple act of condensation releases heat, so the inside of a thunderstorm is warmer than the outsides of the thunderstorm. And hence we have a torrent of warmer air rising through the atmosphere, and it draws more moisture in from the ocean, causing more condensation, more heat inside the thunderstorm. And as this goes on, these storms get a life of their own. So they're entirely driven by how warm is the ocean beneath them, which dictates how much evaporation occurs and how much water vapor is available to be condensed. Therefore, if we have warmer oceans, then you're likely to have more evaporation, giving us more water vapor, and consequently the potential for more clouds to form and more convection to happen. So our concern is, as the temperatures of the atmosphere rise, how will the temperatures of the oceans change? Because if they do rise, there will be that potential for more condensation. Hurricanes will only exist in parts of the ocean where the temperatures are above about 79 degrees Fahrenheit. Less than that, the ocean doesn't evaporate enough water to keep these storms moving. So we look for the areas of the ocean with these warmer temperatures, and as climate change happens, there is the potential that the ocean temperatures would rise, but also the area greater than 79 degrees would increase in size. So there's the potential that these tropical storms could last longer, have more opportunity to grow into hurricanes, and when they became a storm, be at a higher intensity than they would have been otherwise. Along with the warmer ocean temperatures, the other factors involved in hurricane formation include the lack of wind shear. Wind shear is a measure of how fast winds are changing with altitude, both speed and direction. If wind is shearing with altitude and these clouds begin to form, they can form, but they get blown off at the top. They're not able to organize into a vertical column, making the thunderstorm more easily grow. So When we have those seasons of greatest hurricane formation, those typically tend to be seasons with the least amount of wind shear. And those tend to occur in periods that are not El Nino years. El Nino is the oscillation of the ocean in the southern hemisphere in the western Pacific. And those oscillations affect what happens in the North Atlantic. One way it affects that is it causes more wind shear in the North Atlantic. So when we have El Nino off the coast of Peru, it seems to cause fewer hurricanes than in the North Atlantic, and vice versa. When we have the other condition called La Nina in the South Pacific, then wind shear is less in the North Atlantic and we seem to get more hurricane formation. The conditions which form the maximum hurricane strength seem to be those where we have the maximum temperatures in the ocean and where we have the least amount of wind shear. So, in the future, with a warmer general climate, how will that affect those factors? First, we expect that when temperatures of the atmosphere are warmer, that ocean temperatures should get warmer, and we have evidence that that is true. There also has been some evidence in the literature suggesting that the number of extreme hurricanes, Category 4 and Category 5, the most extreme hurricanes, is in fact increasing with time, though this remains controversial. Also, there have been research showing that the amount of total power in a hurricane, wind speeds in the hurricane, measured from satellites over time, has in fact been increasing over the past decades. And this work again remains somewhat controversial, but it's not inconsistent with the concept that if ocean temperatures are getting warmer, if the area that could support hurricanes is getting larger, that makes sense that the power of hurricanes could get greater with time. Of course, the number of hurricanes varies wildly from year to year, largely because of variations in El Nino and La Nina. And these natural fluctuations in hurricane count on top of this relatively small trend in hurricanes makes it difficult for us to really say with confidence that hurricanes are getting stronger or are getting more powerful with time. Unfortunately, we won't know for 10, 20 years yet whether in fact this climate change is causing an increase in hurricane formation. All we do know is that theory supports the concept that hurricanes could get stronger with time. And particularly as more and more people live closer and closer to the ocean, this is cause for some concern. Particularly here in the Midwest, one of the greatest concerns we have about extreme weather is going to be tornadoes. Tornadoes exist in a variety of sizes from F0 to F5. F scale corresponds to the Fujita scale, a measure of the destructive potential of a tornado. An F0 tornado is going to have winds around 100 miles an hour at its core. But an F5 tornado is going to have winds nearly 300 miles an hour and be the size roughly of Central Campus in diameter. Such a storm eliminates virtually everything in its path and contains multiple vortices, each of which has an upward velocity in excess of 100 miles an hour. So it's reasonable to ask, what will happen in a warmer climate? Will we have more tornadoes? Will they be more intense? And will they more likely hit populated areas, as we've been seeing in the last few years? Tornadoes are most prevalent in Florida and in a stretch from Texas through roughly Nebraska known as Tornado Alley. Now, this area of the United States in the Great Plains is popular with tornadoes because it contains the right mix of conditions which produce tornadoes. Tornadoes occur, first of all, in large thunderstorms called supercell thunderstorms. These are storms which are 10 miles across and about 10 miles high. Supercell thunderstorms are going to occur in an atmosphere which is convectively unstable. And what that means is that near the ground, in maybe the first mile or so, is an atmosphere full of moisture, very muggy, hot conditions. Above that is a layer of the atmosphere which is actually fairly cold and dry. And that mix of two layers is convectively unstable in that this layer at the ground contains what you think of as fuel for the storm, and the air above it is cold, so that if something comes along and causes the air to start to rise up, this air will rise with great speed and storms can form very quickly. In addition to the convective instability, in order for a tornado to form, there needs to be wind shear. That is, the air near the ground is moving in one direction and the air above it is moving in a different direction, so that there is a shear formed between these two layers. So that if air is able to start to rise, somehow a thunderstorm forms, what's going to happen is that shear between those two layers, this horizontal rotation, gets carried vertically, and you can imagine that horizontal rotation then becoming vertical rotation. We think that this might be the seed for how tornadoes form in these large thunderstorms. So we have the convective instability, we'd have wind shear occurring out in the Great Plains, but in order to get a thunderstorm of sufficient size and energy to produce a tornado, on top of that you also need a trigger. And that trigger is going to be either some kind of cold front or, more likely, something called a dry line. Now, a dry line is air that's particularly hot moving into air that's pretty hot but muggy. And it might be counterintuitive, but if you have air that's 90 degrees and dry and air that's 90 degrees and muggy, it turns out the air that's 90 degrees and dry is actually heavier than the muggy air. So this hot, dry air coming out of New Mexico and western Texas moves into the Great Plains, pushes the muggy air coming perhaps from the Gulf of Mexico out of the way, and this dry line then can act as a trigger. It can force the air upwards as this hot air moves across the country and just pushes the air in its way upward. This triggers the thunderstorm, carrying that shear with it as it rises, and once these storms start to form, they will grow dramatically and quickly. So a supercell thunderstorm, once initiated, will grow to its full size in less than an hour often. And these are storms then which will basically create their own low pressure system, can produce their own circulation, so they have a flow, a counterclockwise flow around a central point. And that rotation then can become focused on one spot and a tornado can form. Clearly, not many thunderstorms produce tornadoes, thank goodness. But the few that do can produce dramatic tornadoes, everything from an F0, the weakest of tornadoes, through an F5 tornado, which is on the size of central campus of the University of Michigan. Well, another important factor in tornado formation is the jet stream. The high river of wind at the top of the troposphere has regions in it called areas of divergence, which help create that upward motion in the first place in the storm, help this cloud as it starts to rise to sort of carry the excess air off in a high rate of speed. So we do know that tornadoes are best likely to form when we have a jet stream available. So the real question in how climate might affect tornadoes is how would climate affect the jet stream? The jet stream, we know, is caused because the temperature difference between the tropics and the polar regions causes a pressure gradient in the upper atmosphere. And that pressure gradient becomes strongest where the temperatures change the fastest at the ground. If the temperatures were to rise, and we expect that the temperatures rise more in the polar regions than the tropics, it is possible the jet stream would be affected. The great question in tornado research is, will there be more tornadoes in the future? Will they be more intense? Are they more likely to hit populated areas? We do know from past experience that over the last 50 years there are more reported tornadoes than ever before. We suspect that's because there are more people reporting tornadoes. That is, there are more people with video cameras, there are more people living in rural areas, and we have radar that can detect tornadoes that maybe humans won't even see. So our capacity to observe tornadoes has improved. Whether there would actually be more tornadoes in the future is open to speculation. We expect that there will be more thunderstorms in the future. Climate models predict that in the future we will have more precipitation over much of the United States, but it's going to occur in fewer events. That is, long periods of dryness and small but intense periods of precipitation. Now, whether that translates into more opportunities for tornadoes to form, we do not know. But there is evidence that there will be more convection in the future with the additional heat. Today, we can't say with any confidence that there are going to be more or fewer tornadoes in the future because of that. We've been having a particularly rugged summer here in Ann Arbor with high temperatures and heavy rains. The question is this going to continue in the future? We can't say with certainty that this is in fact climate change happening. What we can say with certainty is that the things that are happening are not inconsistent with what our climate models are predicting. So as we look forward, we must be concerned about drought occurring more often and how that might affect temperatures around the country, how it might affect our food supply, how it might affect the occurrences of fire around the United States. Likewise, we need to be concerned about how drought would affect political stability in other parts of the world. And for those people living near shorelines, there's going to be a concern about the potential for increased precipitation and flooding associated with tropical storms and hurricanes. We cannot say with certainty what's going to happen next with climate, but we are concerned that the kinds of things that we're seeing happening these past 10 years or so, the increased temperatures, the extended periods of drought and floods, are truly consistent with what we expect to be happening. And for those reasons, we as atmospheric scientists are concerned about where our atmosphere is going and how that will affect us in the coming years.